All right, I've decided to make this video retroactively, although I've made a video this semester discussing how to calculate the E field due to a single charged particle at some point of interest. I think it's important to talk about when there's more than one charge. So today we're going to discuss what's called the superposition principle, or not to be confused with the quantum mechanical one. This is the classical superposition principle, and we're going to use it for electric fields. And it's something that you're used to from 211. It just hasn't been called that until now. And so kind of what the superposition principle states is that if we're interested in the E field at a certain point in space, and there's multiple charges, we can find the E field caused by each individual charge and find those vectors, and then simply add those vectors to get the total E field at the point of interest. So basically what it's saying is, like, you can ignore one charge while calculating the other's electric field contribution, and then ignore the first one and calculate the second one, and then just sum the results to find the resultant E field. So in this case, I wanted to give an example where everything wasn't just X and Y. So the point of interest is going to be the asterisk here. We're going to find the E field vector at that point caused by both of these charges. So we're looking for the total E field at this specific point of interest. So it's the X and Y direction. And so to do that, we're going to use our handy E field equation. We're going to use it twice. So what I'm going to go ahead and do is I'm going to go ahead and start by just calculating the E field caused by particle one. And you know what, actually, I'm just going to calculate the field strength, and then we'll figure out the vectorial direction later. So that would be Coulomb's constant times Q1 divided by R1 squared in the R hat direction for that particular particle. Remember, the R hat coordinate system moves with the particle. So R hat vector for Q1 is going to be radial outward from Q1, whereas R hat vector for Q2 is going to be radially outward from Q2. All right, so now we can go ahead and plug in numbers. Q1 happens to be, I picked it as 1 times 10 to the minus 6 coulombs. I tend to like the microcoulomb number. It seems to show up a lot. Oh, and I forgot to tell us what R1 was. Oh, I guess I didn't know. Okay, so each tick mark here is going to represent 1 meter. And so in this case, R1 is going to be 2 meters. So we'll go ahead and plug in 2 there and square it. And I probably should have done the calculations beforehand, but I didn't. So I'll just go ahead and do them now. And if I end up making a mistake, it would be appreciated if you found it and shared it with me. So E1, the electric field strength caused by Q1 at this distance, is equal to 2,247.5 newtons per coulomb. All right, then we'll go ahead and do E2. And I'm just going to plug and chug at this point, now that you've seen the process for the first one. And E2 has a absolute value of charge of 2 times e to the minus 6. Of course, it's negative, and we will take that into account later. We need to figure out what R2 is. And to do that, we can use Pythagoras' theorem. And we know, okay, so R2 has an X component of 2 and a Y component of 2 as well. So 2 squared plus 2 squared, I believe that's 8. So R2 ends up being the square root of 8, which is 2 root 2, I think. Yeah, 2 root 2. Okay. So now that we know that, we can go ahead and plug this into our calculators. Or now we've got, okay, Q2 is 2 times 10 to the minus 6. I'm not including the sign of the charge at this point because I'm gonna do that later when I actually draw the electric field vectors. All right, so now we can go ahead and plug in. And let's deal with 2 root 2 first. That's going to be 8, right? Because 2 squared is 4, root 2 squared is 2, 2 times 4 is 8. So 8 in the denominator. So we get, oh my goodness, this is so cool. 2,247.5 newtons per coulomb. I almost can't believe it. It's the same field strength. I'm going to have to calculate it again just to make sure. But that is super cool because this was randomly selected. Yep, cool. So, you know, Q1 is closer than Q2, but Q2 has double the charge. And so somehow it's all balancing out and we're ending up with the E field strength contribution, the magnitude of those E fields are equivalent. All right, so now it's time to draw the vectors, the E field vectors caused by each charge. And this is where the superposition principle comes into play. Okay, so Q2 is a negative charge. And we know that field lines, electric field lines, they sink into negative charges. In other words, the arrow is going to point towards that charge, collinear with the radius. Okay. So there's the E field contribution from Q2. And then for Q1 is a positive charge. And we know that field lines point away from positive charges. So for Q1, the E field contribution is going to look like this. And of course, these two vectors happen to have the same magnitude as we calculated. And so now that we know these things, we would just need to add them up. Okay, so now we just take the vectorial sum of these two vectors. And to do that, we're going to have to break them into components. The nice thing is that the contribution of the E field caused by Q1 is already just in the negative y direction. So E1 as a vector is just going to be 2,247.5 in the negative j hat direction. Okay, and then of course, if this radius 2 goes over 2 and up, goes over 2 and down 2, then that means that this angle is 45 degrees. But well, I guess we'll solve it that way because that's kind of something that we're used to at this point, is using the trig identities to break down components. There are other ways to do it, but let's go ahead and do it this way. So the vector E2 is going to be equal to, so the x component is, it looks like it's in the negative direction, and it's going to be the magnitude of E2 times, right, it's the adjacent to this 45. So that's going to be cosine 45 degrees in the I hat direction. And then it's also has a negative y hat component as well. Like this, it happens to be the opposite side. Not that it matters with 45 degrees, cosine 45, sine 45, both root 2 over 2. So, but we'll just try to be consistent. So in the minus y direction, it's the hypotenuse or the magnitude of the E field in this case, sine 45 degrees in the j direction. All right, so I will just go ahead and get this all into decimals. So E2 equals it has this much of a x direction component, and of course the y direction component is going to be equivalent because sine of 45 and cosine of 45 are the same. But there's nothing wrong with double checking. All right, looks good. So now comes the last step, right? We're just going to take the vectorial sum. So the total E field at the point of interest is just equal to the sum of E1 plus E2, or the sum of E1 and E2, I should say. So we just add like components, right? So only E2 has X component. So here's the X component of the total E field at the point of interest. And then we have to sum the other two, right? So E1 has a J component. E2 has a J component, and they're both negative. And we end up with negative 3,836.7 in the J direction, units in newtons per coulomb. All right, so that's the superposition principle. I suppose just as a review, right, there was no charge here. We were just kind of looking at a point of interest. You know, let's say that we went ahead and we dropped a charge in there, and we'll call it Q3. I can't stress this equation enough, because we've just done all this work calculating the E field. So if I drop a charge in there, the solution should be pretty easy from here. So let's go ahead and say that Q3 is 1 times 10 to the minus 6 coulombs. So I know that the force, the total force caused by the electric field on Q3 is equal to the amount of charge Q3 has times the total E field at the point that we place it, right? So this is what we just calculated using the superposition principle and vector addition. This is what I gave you. Okay, we dropped a charge Q3 in, and this will actually spit out a vector. So this is convenient. Total force on 3 is going to be equal to Q3, which is 1 times 10 to the minus 6 coulombs, times the E field at that point in space, which is what we calculated prior. Okay. So the force is going to point, you know, somewhere in this direction, because we have a positive Q3. If we had a negative Q3, we could just go ahead and plug the Q3 in as a negative, and then the force would point in this direction as opposed to this direction. So for some of these equations, it's all good to plug in the charge as a negative or positive. Just be sure that you pick one for each process, and that you don't accidentally kind of do both at the same time and end up getting the field or the force drawn in the wrong direction. And lastly, you can, in this case, this wasn't actually a negative charge. Q3 wasn't negative. So of course we can, for any vector, we can distribute a scalar into both the components. And so, yeah, that would be the process of finding the force caused by Q1 and Q2 on this charge Q3. All right, I hope this was useful and helps you in your homework and test scenarios. And thank you for watching. I'll see you next time.